The motivation for this research is the need to improve interactive motion forecasting. The current methods in use have limitations, particularly in their ability to capture the joint distribution over multimodal futures effectively. This is a significant issue as it can impact the accuracy and reliability of the predictions made. Existing approaches also struggle with latency-critical settings. This is due to their inability to generate a sufficient number of samples from the model quickly enough. Furthermore, these methods have not been able to surpass the previous top entry on joint map with a limited number of rollouts. This indicates a need for a more efficient and effective method. The approach proposed in this paper aims to address these limitations. It leverages multi-agent rollouts over discrete motion tokens, which allows for a more comprehensive and accurate representation of the joint distribution over multimodal futures. This method also generates a sufficient number of samples from the model, clusters down to k=6 modes for evaluation, and uses 512 rollouts per replica for final leaderboard results. The proposed method has shown promising results, surpassing the previous top entry on joint map with just 32 rollouts, and establishing new state-of-the-art performance on the WOMD Interactive Prediction Challenge. These results indicate that the proposed method is a significant improvement over existing approaches and has the potential to greatly enhance interactive motion forecasting. The existing methods for interactive motion forecasting have certain limitations that this paper aims to address. One of the key issues is their inability to effectively capture the joint distribution over multimodal futures. This is a significant problem because it limits the accuracy and effectiveness of motion prediction, which is crucial in various applications such as autonomous driving and robotics. Moreover, previous methods have struggled to perform well in latency-critical settings. This is a critical issue as real-time response is often required in many applications of motion prediction. The inability to handle such settings can lead to delays and inaccuracies, which can have serious consequences. Another limitation of existing methods is their inability to surpass the previous top entry on joint map with a limited number of rollouts. This is a measure of the model's ability to accurately predict multiple possible future states, and a higher score indicates better performance. The inability to achieve high scores with fewer rollouts suggests that these methods may not be as efficient or effective as desired. To address these issues, the authors of this paper introduced a new method that generates a sufficient number of samples from the model and clusters down to k=6 modes for evaluation. This approach allows for a more accurate representation of the multimodal future distribution. For the final leaderboard results, the method uses 512 rollouts per replica, demonstrating its efficiency as it surpasses the previous top entry on joint map with just 32 rollouts. Furthermore, the authors propose leveraging the trained model in model-based planning frameworks, which allows for the formation of a search tree over the multi-agent action rollouts. This is a novel approach that can potentially improve the performance of the model. Additionally, the authors plan to explore distillation strategies from large autoregressive teachers, which could enable faster student models to be deployed in latency-critical settings. These new strategies and techniques are key to improving the performance of interactive motion forecasting models. Section 1. Problem formulation and approach. The authors of this paper have aimed to enhance interactive motion forecasting. They have formulated the problem as one of capturing the joint distribution over multimodal futures. To tackle this, they have proposed a method that leverages multi-agent rollouts over discrete motion tokens. This approach is a departure from previous methods that relied on trajectory anchors or static intention points. Section 2. Methodology and experiment design. The authors have designed a method that generates a sufficient number of samples from the model. They have then clustered these down to k=6 modes for evaluation. The model uses 512 rollouts per replica for final leaderboard results. The authors have designed experiments to evaluate the model using performance metrics and the WOMD Interactive Prediction Challenge. They have also conducted an ablation study that varies the number of rollouts generated and evaluates single replica performance and ensembled model performance. Section 3. Improvements and innovations. The proposed method has shown significant improvements over previous approaches. It has surpassed the previous top entry on joint map with just 32 rollouts and has established new state-of-the-art performance on the WOMD Interactive Prediction Challenge. The model can also be leveraged in model-based planning frameworks and can form a search tree over the multi-agent action rollouts. It can learn amortized value functions from large datasets of scene rollouts and can be deployed in latency-critical settings with distillation strategies from large autoregressive teachers. These innovations represent a significant step forward in the field of interactive motion forecasting. Technical results. The proposed model demonstrates significant improvements in performance metrics with the addition of more rollouts. This indicates that the model's ability to forecast interactive motion effectively increases with the number of rollouts generated. With just 32 rollouts, the model is able to surpass the previous top entry on Joint Map, demonstrating its efficiency and effectiveness. The model establishes a new benchmark in the WOMD Interactive Prediction Challenge, indicating its superior performance in interactive motion prediction. Implications of results. The results suggest that the proposed model is highly efficient, requiring fewer rollouts to surpass previous top scores. The model's state-of-the-art performance in the WOMD challenge implies its potential for practical applications in interactive motion forecasting. Ablation study results. The ablation study involved varying the number of rollouts generated, evaluating the performance of a single replica and an ensembled model, and computing standard deviations for each metric over 8 independently trained replicas. The study found that performance metrics generally improve as additional rollouts are utilized, indicating the model's scalability and adaptability. Implications of ablation study. The ablation study results suggest that the model's performance can be further optimized by adjusting the number of rollouts. The study also indicates that the model is robust, as it performs consistently across multiple independently trained replicas. Key highlights of the paper. 1. Key insights. The paper introduces a novel method for interactive motion forecasting that leverages multi-agent rollouts over discrete motion tokens. This approach is capable of capturing the joint distribution over multimodal futures, which is a significant advancement over existing methods. The model can be utilized in model-based planning frameworks, form a search tree over the multi-agent action rollouts, and learn amortized value functions from large datasets of scene rollouts. It also offers potential for deployment in latency-critical settings through distillation strategies from large autoregressive teachers. 2. Key contribution. The paper's main contribution is the development of a model that generates a sufficient number of samples from the model, clusters down to k=6 modes for evaluation, and uses 512 rollouts per replica for final leaderboard results. This model is a significant improvement over existing methods, which may struggle with latency-critical settings and may not surpass the previous top entry on Joint Map with a limited number of rollouts. 3. Key idea. The central idea of the paper is to improve interactive motion forecasting by generating a sufficient number of samples from the model and clustering them down for evaluation. This approach allows for a more accurate representation of the multimodal future distribution. 4. Key results. The model demonstrated improved performance metrics with additional rollouts and surpassed the previous top entry on Joint Map with just 32 rollouts. It also established new state-of-the-art performance on the WOMD Interactive Prediction Challenge. 5. Key conclusion. The paper concludes that the proposed model offers a promising avenue for future work, including its potential use in model-based planning frameworks and its ability to learn from large datasets of scene rollouts. The model's ability to be deployed in latency-critical settings through distillation strategies from large autoregressive teachers is also a significant conclusion.